All right, now we're going to do the same thing we did in the previous video, but now we're going to do it for two sample confidence intervals. So for two samples, we have a two sample t, a two sample or two proportion z-test, and a linear regression t-test. Those are what we would get with a two sample. Also, what I should put on here is match pairs, which is just a one sample t. Now, keep in mind with the two proportions, we use the formula for proportions for confidence intervals, not the one that we use with hypothesis tests. Here's the first one. We want to test the effect of high protein diets on weight gain. 12 juvenile rats are fed a high protein diet and their weight gains are given below. As a comparison, another 12 rats were given a regular diet. Their weight gains were below. Find a 95% confidence interval for the difference in their weight gains. Now, are these the same two rats? I think you should see here, no. If they were the same rats, we could do a match pairs test. But since they're not the same rats, these are two independent uh, values. So we have uh, independent t. So we're going to use our formula for one. So what we want to do is we want to subtract our means, add and subtract our since we don't know our population standard deviation, that would be a t, and then we're going to multiply that by the standard deviation of 1 squared over n plus standard deviation of the second one over n2. All right. Now when we're doing this, we'll want to subtract our x bars. So we got 121.6 repeating minus 100.3 repeating plus or minus your t star. Now there's a conservative way to do this where we take 12 minus 1 to find our degree of freedom with our t star, or we can use our calculator and just do a two sample t interval, and we could get a more specific degree of freedom. Now, when I use my calculator, and I'll show you how to do this in class, I got a degree of freedom of 21.3. Now, we could have also done a degree of freedom of 9. We just have to report that we'd use a degree of freedom 9 and get the value there. So for our t star, we could use 21 for our degree of freedom. So if I use 21 for my degree of freedom, I can look back at my chart here. 21, 95% confidence interval, that's 2.080. So I'll come here, 2.080, and then square root. Standard deviation of the first one is 19.4-ish over 12, plus the standard deviation of the second one is 16.2 squared over 12. And now we do the math and figure the rest of this out. So our value, we subtract 121.6 minus 100.3, and we get 21.3 repeating is our point estimate. And then we find the standard deviation here, or standard error, by multiplying all this together. And when I do all the math, I get 15.17 or 18. So now I just subtract that and add that to our point estimate, and that'll be our confidence interval. So 21.3 minus that answer, I get 6.12. 21.3 plus 15.17. I get 36.5 or 47. All right, this next problem. A study is done by comparing male and female voters in Oregon. The specific question asked of members of both groups as to whether they voted for Romney or Obama in 2012 presidential election. we wanted to estimate the difference in proportions of women who voted for Obama and the proportion of men who voted for Romney. Uh, we take samples of 5,288 voters. Of the 3,017 women, 1,642 said they voted for Obama. Of the 2,271 men, 1,176 said they voted for Romney. What is the 90% confidence interval for the difference in proportions for the people who voted for either? So it's men who voted for Romney and women who voted for Obama. So if we're going to do difference in proportions, we take both our p hats and subtract them. Since it's a proportion, we have to use our z star, and we're going to take our one proportion times 1 minus that p hat all over our n1, and then we're going to add it to our second one over n2. All right, so now we just have to do the math. All right, so now when we subtract the two proportions, I get 0.544 minus 0.5178, so that 518 plus or minus z star for 90% confidence interval is 1.64 times the proportion 0.544 times 1 minus 0.544 all over our first n, which is 3,017, plus our second one, which is 0.518 times 1 minus 0.518 all over our second value, which is 2,271. All right, now when we subtract these numbers, 0.544 minus 0.517, or 8, I get 0.026. So that is our point estimate. And now I have to do the math here. I got 0.023. So if I go subtract from both sides, that 0.003 all the way to 0.049. So somewhere between almost no percent up to almost 5% would be the difference between those two groups. Now we have one more quick one. Perform a 95% confidence interval for the slope between the numbers of beers drinking and blood alcohol content. We got the beers, the blood alcohol content. Now for a test like this, you take your slope plus or minus t star times your standard error for the slope. Now from our regression equation, it tells us our slope is 0.0179, so it's 0.018, plus or minus our t star. Now here, since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, since our n is 16, our degree of freedom is 2 less than that because it's a linear regression. So we got 14. So we find t star at 14. And I found that to be 2.145. And now the standard error of slope is this next number here, which is 0.002402. So now we just figure this out, 2.145 times 0.002402. So we can add or subtract 0.005 from this value. So it's going to be 0.013 all the way up to 0.023. And we think the slope is going to be somewhere in there. All right, from this, hopefully you can do there on your own.